All right, so this time it does pick up. All right. So I'm just going to go back to the homework assignment so I can look at the actual code, and then we'll start from there. Okay, do a preview, and I think it's question 4 that has the code. Nope. Question 2. Nope. Question 3. Yep. Question 3 has the source code. All right. And I'll do it in a mouse pad. Okay. Okay. Just double checking it still looks okay. All right, so we'll go ahead and implement the Fibonacci subroutine. F is the entry point label of Fibonacci. And then do you want to use labels? Yeah. Okay. So in this case, we do not have any local variables. So return address has a definition of 0 because the stack pointer should be pointing at the return address. So that will make n 1 byte after the return address, like so. And so now we can implement the only statement, which is on line 3. Line 3 is a ternary operator, or the expression of the return value is a ternary operator. So we have to evaluate the condition first. So we do LDIA with n, add d to a. So now a is the address of n, which is not what I want. I want the actual value. So I need to dereference it once. So now a is actually parameter n. We have to compare to 2. So we do LDIB with 2. And now we have to choose, which way do we want to do it. Do we want to specify if it's greater than or equal to, then go to the else, or do we want to just say if n is less than 2, we go to the then. So there are 2 ways to do it. They're about the same. Both will involve 2 jumps. One will involve 2 jumps and 1 additional label. The other one is just 2 jumps. So we can do it either way. So in this case, I'm just going to compare n to 2. Okay. So this is n minus 2. So if we are looking at n minus 2, if it is less than, then we want to go to the then case right away. So that means if it's if we use JCI to go to the then branch, that means JMPI to go to else. Unsigned. Yeah, we are not assuming it is actually unsigned in the parameter. So the then case is easy because it's already done. Okay, because we just need register A to have the value of n, which it already does. So the then doesn't really have anything to do but to go to the return label of the entire thing, or go to end if you want. So end if is all the way here, and then we have else. The else is the recursive one. We are returning the sum of the return values of f of n minus 1 and f of n minus 2. So we'll take up the first one first. Register A already has n, so decrement A will make A equal to n minus 1. Is that okay? And we'll push it on the stack. And then we'll do the call to Fibonacci. So we do a LDI A with dot 6 plus decrement D STDA JMPI to the subroutine. When it comes back, we have to increment D to deallocate the argument. but then we have to redecrement D to remember the return value of this invocation. So now we have the stda. So we are pushing the return value of f of n minus 1 on the stack. Because if I don't do this, the next invocation is going to overwrite register A, then I would have lost the return value of the first call to Fibonacci. Okay, so this is kind of important. This is also why I use the 5-7-12 sample program, because it has exactly the same nature, even though that one is not recursive. Okay, all right. But at this point, we also have to add one more to the stack offset, because now we have one additional thing on the stack. The stack pointer is no longer pointing to the return address. It is pointing to 1 byte below the stack pointer. So we have to keep that in mind. So now we have LDI A with n again, but this time it's n 1 plus, because it is now 1 more bytes off from where the stack pointer is pointing to. So add AD, and then we do LDAA. Okay, so now this is n, so A is n again. So the other way to do this is, before we increment D on line 21, we could have retrieved that byte into a different register, something other than A, because that is supposed to be n minus 1 on the stack after the first call to the subroutine. But the problem is, there's nothing preventing the subroutine from changing the argument, changing the parameters, because a parameter is really just like a local variable, except it's initialized by the caller. So I don't want to count on that. Okay? So this way it is more sure, more secure. Okay, so now we decrement it twice, decrement A. So the A is now n minus 2. So now we go through the same motion, pushing on the stack, decrement the stack pointer, store to where the stack pointer is pointing to, and then we do LDIA dot 6 plus, decrement D, STDA, JMPI to F again, increment the stack pointer. So at this point, we have one thing on the stack and then one thing in register A. Okay, so at this point, D points to the saved return value of f of n minus 1. A has the return value of f of n minus 2. So we need to restore, or at least retrieve. So we're going to retrieve whatever the stack pointer has to register B and then increment D. So this is basically the same thing as popping return value of f of n minus 1 to register B. Then we add register B to register A, and then we are done. So now we can go to, we now define the end if label, where we just perform the return. So LD B with D, increment D, JMPB, that should do it. Okay? All right, so this is the subroutine, and we need to test it. So to test this, the minimum we have to do is to initialize the stack pointer, and then we set up a particular parameter. So so the best way to do this, I would test it with 0 first. 0 and 1 are the first ones that we need to test it with, to make sure that the non-recursive calls are okay. So I want to test it like step by step. So we have, we just push a 0 on the stack, decrement D, STDA, LDIA dot plus 6 plus, decrement D, STDA, JMPI to F, and then when it comes back, I'll just increment D to balance the stack, and then we're done here. So I'm not even storing it to anything. I'm just checking register A to make sure that it is returning 0. Is that okay? So that's my code, and now we go back to the assembler. Okay. Okay, looks like everything is good. Uh-oh. It doesn't like... Yeah, and it even tells me that it was defined here. Did I do that here? Oh yeah. Yeah, that was good thing the assembler caught it. Okay. So this is not needed. This is extra. There we go. Everything should be good now. Yeah. So download as. And then we'll, oh, that terminal is done. Okay. So I'm just going to do a Control K here, and then check that the register A is 0. So it's good. The stack is balanced. It's all good. All right. So without actually going through the assembler again, I can tweak the memory of the RAM to test other cases. So I'm looking for this load A with 0. I just want to change this 0 to something else. So now I have a different test case. Yeah. So that would be location 3. So 0, 3 needs to be changed. But before I do that, I also need to reset the processor. If the clock is low, I can just click the reset to the processor side without resetting RAM. But that's tricky. That's why I don't do it in class. So I want to change this location to 0, 1. And now it's testing the Fibonacci of 1. So Control K again, go to the register, and register A is 1, so that's good. And the stack is still balanced, so that's good too. Clock is low, so I can now directly change this, reset the processor by clicking the reset button, and then change this location to 0, 2. So f of 2 is recursive, but it also has a value of 1, because f of 2 is f of 1 plus f of 0. F of 1 is just 1, f of 0 is 0, so 1 plus 0 is 1. Okay, but we know it's recursive this time. So we'll go ahead and do a Control K. It's done. Check the return value first. F of 1 is 1, stack is balanced. Okay, that's all good. But then this time we can also check the stack, because the stack should tell us that this time it was recursive as opposed to the previous time. So when you look at the stack content, this is 2, which is the parameter to the first invocation. This is the return address to main, okay, which we don't call main in this case. This is the saved return value of f of 1. And this is the argument to f again when we compute f of n minus 2. And then this is the return address of the second invocation of f in the subroutine. So if you look up location 3, 5, that should go back to it should continue after the second call to Fibonacci. So you want to test 5? Yeah. Yeah, sure. Why not? So it will use a little bit more. So each invocation takes up 3 additional bytes. So this time it will take up, the first one only takes up 2, and then each consecutive one will take up 3 bytes. So we have 2 plus 4 times 3, so 14 bytes on the stack should be used. All right, so reset the processor, change the Fibonacci to 0, 5, Control K. Okay, it's all done. Double check. Yep, it is all done. we look at the image. So it used up less than that, right? It used only up to here, so it only used up to 13. No, 11 bytes, because each row has 16 bytes. Assuming all of these zeros are not used, because the last thing it pushed should be a return address, which is non-zero. So it's from here. So it's only using 11 bytes. And that's because the first recursive call is it doesn't use up the additional byte. It's only the second one. And the question is, does it return the correct value? So f of 5, according to this, is 5. Is that right? We'll check. Yeah, so according to this, f of 5 should be 5. Yep. Which is coincidental because the argument is 5 as well.
Yeah.
So we can give it something more complex to do. So this is 5, 6, 7. Let's try f of 8.
Yeah.
Which will take a little bit longer. Yeah, f of 8. Okay, there we go.
Where I was messing up was coming out of the first implication of f. And not deallocate everything. We're not storing that value on
I see. Yep, then you lose it, right?
Yeah.
Okay, so it's checking f of 8 this time. It's okay. It's done. Yeah. Yep. 1, 5 is in hexadecimal. So it's 16 plus 5, which is 21. Was it actually 21? Yep, it was 21, so we got it done. Any questions? So you just did not save the return value of the first call, okay?
That's right.
Okay.
Thank you.
Sure, you're welcome.
I would like my example is like I actually am enrolled in the Tuesday Thursday.
Mm-hmm.
So I was just like